All right, guys. Up till now, let's review what you have learned to do with integration. Now, this is a fairly difficult problem here, but at this point, I hope you understand that you could use u substitution. And if you do, let's make u equal to sine x, then du is going to equal cosine x dx. Well, it's easy to account for all the parts of the puzzle here because sine squared x becomes u squared and cosine x dx becomes du. And now you realize, okay, that one's pretty easy to integrate. Well, the same thing is true here. If I ask you to let u equal x cubed plus 3x squared, du becomes 3x squared plus 6x all dx. So of course when I look at the original problem, I could say, well, let me write it as 1 over u times x squared plus 2x dx. You all are used to me breaking it into parts like this. And of course, we have to figure out, is there a way for me to rewrite the x squared plus 2x dx somehow with just u's? So I'll look back up at my du term and realize if I simply factor out 3, I'll have x squared plus 2x dx, which means I could rewrite my integral as 1 over u, and the x squared plus 2x dx is going to be du all divided by 3. And so you know that a more usable way of writing this integral is 1/3 times the integral of 1 over u du. And you know how to integrate that now using ln of the absolute value of u. So on both of these problems, the package works out pretty nicely. I'm giving you everything you need. Well, let's take a look at 4 examples that don't work out pretty nicely. On number 3, for instance, you might look at it and say, oh, okay, well, maybe I ought to let u equal x squared. But then du would be 2x dx. And then you ought to say, well, the problem is, what do I do with cosine? Because I can't somehow get cosine x out of what I've got for u and du. So then you might try letting u equal cosine x. But then du would have to be negative sine x dx. And again, you don't have anything in the problem that would allow you to put in like dx. You can't put it as du over negative sine x because that still is going to give you too many letters. So that's not going to work. And some people say, well, just let u equal x. If you do that, guys, all you're doing is doing a variable swap and you're making it u squared cosine u du, which makes the problem no easier. So that's not working. So the same kind of thing is true on all 4 examples I've shown you. So what we need is a brand new method. There are actually 2 methods that we're going to get into. The first method that we'll talk about is tabular integration. Now it's important, tabular integration is when you're integrating a product, and you'll notice here I've got the product of f of x times g of x. So you've got 2 different functions. Well, that's what you had on number 3. F of x was x squared and g of x was cosine x. On number 4, f of x is x, g of x is e to the negative x. On number 5, f of x is x cubed minus x squared, and g of x is 2 to the x. On number 6, f of x is x, and g of x is going to be ln of x. So far, all 4 of the weird problems I've shown you do fit this f of x times g of x model. Now, tabular integration is really handy if one of the 2 functions is polynomial. So that's what I'm calling f of x. The reason is polynomials, look here, dissolve whenever you do repeated differentiation. So on number 3, f of x is your x squared, and if you differentiate it, it goes to 2x, and if you differentiate that, it goes to 2, and if you differentiate that, it dissolves to 0. On number 4, f of x is x. When you differentiate x, you get 1, and when you differentiate 1 again, you get 0. Remember, we're looking for a polynomial that dissolves to 0. All of the x cubed minus x squared would be f of x on number 5. Remember, the first derivative would be 3x squared minus 2x. The second derivative would wind up being what? 6x minus 2. The next derivative would be 6. The next derivative would be 0. So, ditto here. You're going to differentiate from x to 1 to 0. So, on all the problems I've given you, one of the two functions is a polynomial that you could repeatedly differentiate until it dissolves to 0. Now, the other requirement for tabular integration is that g of x has to be a function which is easy to repeatedly integrate. Or, let me say it this way, it's got to be a function that you can get antiderivative after antiderivative after antiderivative. So, I know, for instance, on number 3, if you look at cosine x as being your g of x, the antiderivative of cosine x is sine x. The antiderivative of sine x is negative cosine x. The antiderivative of negative cosine x is negative sine x. So see, you can go up that ladder real quickly. On number 4, the g of x will be e to the negative x. Its antiderivative is negative e to the negative x. Its antiderivative is negative e to the negative x, which is back to positive e to the negative x. Of course, on 2 to the x, its antiderivative is 2 to the x over ln2. Its antiderivative is 2 to the x over ln2 over a new ln2. And so you can go on and on and on. So let's take a look at your worksheet at this point, and let's see if you can figure out which ones are easy to use tabular integration.